Okay. Okay, very welcome to all of you. And today, actually, we will have a target of, of leading this discussion to a very important concept in condensed matter physics, what is generally known as integral quantum Hall effect. So before we will jump into the integral quantum Hall effect, it becomes essential for us to realize the condensed matter physics at the bulk level. We have to understand, we have to basically revise some of the important concepts in condensed matter physics. Because you see, when you do condensed matter physics, there is basically mixture of theories involved. Somewhere you are using pure classical theories to understand the materials, why certain materials have certain properties. If we boil down this argument, if I say materials, solid materials, okay, if I tell you, what do you think about the solid materials? How will you answer this question? You will have different ways of answering this question. One of the fundamental way will be, you will say, sir, solids can be classified into three categories. You can have a solid which can be a very good conductor of electricity. You can have a solid which is very bad conductor of electricity. And you can have a solid whose conductivity is between an insulator and a metallic conductor, right? So this will be your answer, or someone else will come and he will say, come on, okay, I can classify the solids. I have a different argument. I can say that some solids have a very good magnetic behavior. Some solids have a very bad magnetic behavior. And I can classify solids based on the properties of magnetism. I can say some of the solids are diamagnetic in nature, some of the solids are paramagnetic in nature, and some of the solids are ferromagnetic in nature. And then you can have ferrimagnetic, then you can have anti-ferrimagnetic properties. So you are trying to classify the solids based on these properties. But what we are actually doing there, and what are the basic arguments of that bulk matter physics, a physics in which we talk about those lattice points, then we generate those Brillouin zones, right? And then we talk about the band theory, then you have the energy distribution, then you say, come on, there are bands in solids, you have valence band, you have conduction band. If there is an overlap between the valence band and conduction band, you call it a metal, okay? If the overlap is less, you call it a semiconductor. And if there is no overlap between the valence band and the conduction band, you will use this category for an insulator, right? So this is the argument. But again, let's go back to this framework. Let's try to understand that what we have assumed when we have discussed this level of physics. The physics at the bulk state. So the very first argument here is, how can I identify something what I call as bulk? Okay, so anything. So when I talk about the bulk, if your material has the number of atoms of the order of 10 to the power of 23, and you know this power belongs to Avogadro's number. And 10 to the power of 23 is a very large number. Okay? So any metal, but can you see it? No, it's a very small quantity. This is your bulk material. A material which has minimum number of atoms or molecules equal to 10 to the power of 23. This is your bulk material. 10 to the power of 23 is a very large number. If you rightly remember, if I tell you what's the age of the universe, according to the present calculations, you will say it has lived nearly 13.8 billion years. And all of you know, billion means 10 to the power of 9. And here, I have Avogadro's number, 10 to the power of 23. Now you can imagine the longevity of this number. This number is very, very large. So most of the things that you are doing at this level, the chemistry that you are doing in the laboratories, the reactions that you are manipulating in your laboratories, they are happening at the bulk scale. And most of the bulk scale is based on classical laws of physics. But at the same time, we use quantum mechanical approach to the condensed matter physics. Okay? You have a framework of quantum mechanics for this kind of solids, for these kinds of solids. Okay? Where the number of atoms is more than 10 to the power of 23. And can you tell me the very fundamental models that you discuss about these materials in quantum mechanics? Yeah. You have quantum mechanical free electron theory. Okay? And then you have nearly free electron theory. Then there is tight binding approximation. Then there is Cronin-Penny model. Okay? All of these models, they are trying to explain you the properties of these materials. But keep one thing in mind. The number of atoms involved in these materials is more than that of the Avogadro's number. Now, what does it mean? How will I say that I'm dealing with bulk matter? I'm dealing with bulk matter. I'm dealing with the condensed matter physics that involves these models that I talked about. The very first important argument here is that if you have a solid and you are inside the solid, suppose your size is as equivalent as that of an atom or an electron, and you are inside that material, it is assumed that you will never see the boundary of this crystal. You will never encounter a boundary of this crystal. You are in a crystal which has, say for the sake of argument, 10 to the power of 23 atoms. When you are inside this material, wherever you go in the material, you will never see the boundary of this material. Are you getting my point? Yes. This is the basic argument. So, you have a continuous wave. You have an electron which is never going to see the edge of this universe. It has become an universe for this bulk matter. Are you getting my point? So, what's happening here? What is that we can exploit here? We understand that this electron is never going to have the edge. It will never reach the boundary of this crystal. But we exploit what? What we exploit? We exploit the crystalline nature of this solid. We say, come on, there is periodicity within this solid. isn't it? And you start with your formal Schrodinger's wave equation. And when you write down the solution of that Schrodinger's equation, what you do? When you discuss the Cronin-Penny model, what you do? Yeah. What you do? The first important thing, if somebody tells you what's the difference between a bulk matter and something what is called low dimensional physics, something that's called a nanomaterial, what is the difference? I think the first best answer to that question is that a material can be considered bulk if electron will never see the boundary of that material. For that electron, he is in an infinite C. But that C is what? That C is periodic. What is that? It is this periodicity that we exploit. How we exploit it? We exploit this periodicity when you write down the solution to the Schrodinger's wave equation. And what is the solution for the Schrodinger's equation here? We use a solution like psi of x equal to u k of x e to the power of I k dot r. Isn't it? And what is this u k? What is it? Come on, you have done it already. We are revising our past. This is called block function. This uk is called block function. Right? We call it block function. And this block function has a very beautiful character, because when you add something to this block function, it returns back. But one thing is important here. What you assume here is, for this electron has to move from minus infinity to plus infinity. There is no door, there is no window. An electron can never imagine to be on the edge of the crystal. Now let us think it in a bulk sense. We are humans living on a planet. We are living on planet Earth, isn't it? But we understand the planet Earth is in the solar system. And your solar system is in the Milky Way galaxy. And if I assume this Milky Way galaxy as a crystal, can I imagine that I will reach to the boundary of the Milky Way? The same thing is happening in the bulk materials. The mathematicality that we have, we exploit our mathematical solutions in such a way that electron is never going to be on the edge of that crystalline system. Are you getting my point? Never, ever, and ever. So this is your bulk material. Okay? This is your bulk material, and you have realized the most important part of it, and that is that the electron inside this crystal will never see the boundary. And what it leads us to. Now when I use this solution in the Schrodinger's wave equation, what I obtain? I obtain the bands. You remember? When you take the one-dimensional solution, you have to solve that very big slaughter determinant. We don't solve that, we directly write down the solution of that determinant. Yes. Okay? And then we come up with the final equation. And that equation tells me, come on, because there is no boundary, you are not able to differentiate between the two energies. You have a valence band. And what you assume in the valence band? You assume that there is continuity in the energy in the valence band. that there is continuity in the energy in the conduction band. You have a band here. You are not talking about the individual atoms having individual energy levels. You take a continuum. Only then you are able to solve the Schrodinger equation and reach out to that solution. Got my point? Got my point?
Yes.
So what's the key here again? The key is your electron is in a universe where this electron can never see the boundary of that universe. This is what is called as the bulk matter. Okay? Now you have a bulk matter. Now you have a bulk matter. And this bulk matter is in the form of a thin plane sheet. Okay? A thin plane sheet. Something like this. And in this plane sheet, it's a conductor. And what I do is, I allow the current to pass through it. Okay? It's a very thin sheet of plate. Okay? I'm not saying it's two-dimensional. It's thin sheet. Thin means it's bulk. What is it? It's bulk. And what you are doing here is, you are using a thin sheet of metal, say, I'll start with that. You allow the current to pass through it. When you allow the current to pass through it, what moves in it? It's electrons. So, the electrons have a motion. And what you are doing is, you are applying a magnetic field. You are applying magnetic field to this thin plane sheet. Okay? When you apply the magnetic field, what you see is, you see that you have generated a voltage between the edges of this sheet. Okay?
Yes.
And what is that voltage? That voltage is called Hall voltage. We understand the basic science of this experiment. What is happening? You have electrons. All of you know that whenever an electron is in motion and you apply magnetic field to it, what is going to happen? It changes the direction of the motion of these electrons. It influences the direction of motion of these electrons, and you can resolve the directions using Fleming's right-hand rule. And you can exactly predict in which direction the electrons will move. Now, say for the sake of argument, I will not go into the components, you understand that, X, Y, and Z. I'll not go there. I'll just assume that you apply the magnetic field and you develop a negative charge in this side, which you can actually obtain by using the Fleming's right-hand rule. Okay? And what you obtain? You obtain a negative charge on the one side of this plane sheet. And this should automatically give birth to the positive charge on the other side. Now, if you see a gap between the positive charge and the negative charge, that means there is potential difference. That means there is voltage. And this voltage is transverse in nature. We call it Hall voltage. It's a transverse Hall voltage that develops across this plane sheet of charge. And the reasons for that is, you are suspending your electrons in a magnetic field. And magnetic field orients the electrons in the one side, developing something called as voltage, a transverse voltage, and that voltage is called Hall voltage, isn't it? Okay, so you have magnetic field, and at the same time you have electric field, and you have a better knowledge about the force experienced by a charged particle. When you have a charged particle in magnetic field, what is the force? Yeah, come on. What is that? F magnetic. It is QVB. I'm excluding sine theta because I'm already using my magnetic field in perpendicular direction. And what is this V? This V is the velocity. And since you're talking about this conductor in two-dimensional plane, you have electrons, they are moving, so they have the velocity. And what is that velocity that we call in terms of conductors? We call that as drift velocity, isn't it? So what will be this V is basically Vd, right? And we know from our common understanding of physics that the current flowing in this conductor is ENAVD. Now this E I will replace with the charge. Okay, so this is QNAVD. Are you getting? So can I replace this Vd from this equation? Yeah, I can do that. So what am I going to get is Fm is Q. Instead of Vd, I will write I Q. No. It is divided by Qn and A. Now, what is this A? A is the area of, it's not the area of this kind of thing. It's the area of the cross section. Okay? So you have that, you choose a plane section here, and that section has area A. And between these two edges you have a length, and that length can be treated as D. Right? Okay? So this D is the length between the positive and the negative side, what we call as Hall voltage, right? So what do you expect from this equation? So this is my magnetic force. This has set up a voltage. When you say it has set up a voltage, it has given birth to the electric field. And what is that electric field defined as? Electric field is force electric by charge, isn't it? Okay? So what do you expect? When you are performing this experiment, what do you expect? You expect an equilibrium. And at equilibrium, what's going to happen? At equilibrium, the electrostatic force will be equal to the magnetic force. So F electric is what? It is QEH, isn't it? And F magnetic is what? It's I by QNA. VD is gone, Q is there. Have we done something wrong here? Yeah. Okay, I'll not go with this. Okay, I'll cut it. Let me make it simple now. Okay, so this is your FE. Okay, and FE is QEH. And Fm is QVDB. So Fm is Fe. So what is Fm? That is QVDB equals QEH. This Q and Q is gone. Let's do it this way. And I will replace this Vd by that relation. So what will be that? That will be current by Q and A. And then you have B here equals EH. You see, we are doing it in a very, very pure classical fashion. Assuming that you have a sea of particles, okay? For an electron is never going to see the edge of this universe. And we are calculating an equilibrium situation. And here we are calculating the Hall voltage. So this is current by Q and A, B equals EH. Okay? Now what is this EH? It's the electric field. And this EH is a result of what? It's the result of Hall voltage. So how can we define this EH? EH is VH by D, isn't it? This is a general relation between the electric field and electric potential, right? So if you want to correlate between the electric field and electric potential, you have to incorporate that distance, okay? So that's here. So what do you get out of here? What do you get out of here? Instead of EH, I'll be using VH. So VH by D. So I'll have an equation, yeah? It will be I by QNA. B is equal to VH by D. Fine? Now you see, this is current by area. This is called current density. Okay? So for current and area, I can use J. Then you will have B divided by QN equals VH by D. So I can get this D on the other side. So what is this? This is your Hall voltage, isn't it? This is your Hall voltage. Okay. Now what we do, we define an important parameter that gives us the measurement of the response of your sample when you are placing your sample in this magnetic field. Now see, this experiment is happening at the room temperature. This is all happening at the bulk level. It's all happening at this bulk level, isn't it? And what's going to happen? What do you expect now? So you have this equation. You define something called as Hall coefficient. And how do we define it? We define it as RH, and this is E by BJ. You can keep those components, okay? Because of Fleming's right-hand rule, you can actually detect the direction of electric field, the direction of magnetic field. You can detect them, and you can right here you can have probably it can be EY, BZ, and JX. Okay, so that will suit your geometry. You can do that. So this is called what? Hall coefficient. So Hall coefficient is basically giving us the measurement of the response of the sample. How this sample is responding to your magnetic field that you are applying on it. That's given by the Hall coefficient. And what is this E? This is EH, isn't it? Okay, this EH can be written as VH. Okay? It can be written as VH by D. You can write it here VH by BJ and D. Okay? But we have calculated VH. How much is it?
FH equal to V by D.
Yes.
FH वहाँ पर हमने 8 फीट लिया ना ये हॉल इलेक्ट्रिक फील्ड ऊपर.
Yeah, yeah.
हाँ ऊपर जो फॉर्मूला है.
Yeah, that's fine.
ऊपर आएगा ना FH. फोर्स जो होता है वो हम लिखते हैं.
No. Force is defined as QEH. Okay? So EH is F by Q. Okay? So but then we know actually the relation between the electric field and the electric potential. So that equation is written here. This is EH equals VH by D. Now, I don't know where am I. Okay, can I move on here? Can you tell me what I can write here now? So RH, yeah, is VH. Give me the value of VH. What was that? Yeah, what was that? BJD. Yeah. Did you write that? What was that? Come on. BJ divided by? Yeah, this is what I wanted. Okay. So I have used the value of Hall voltage, and you can see this and these terms will cancel. So what you got? You got the Hall coefficient, and this Hall coefficient is what? It is Qn. What does it mean? What does this equation tell me? I defined this Hall coefficient. I told you that it's telling me how your sample is responding to your external environment. You are applying the magnetic field. Okay? And you see, this Hall coefficient is independent of the geometry of your sample. It is not seeming to be dependent on the length of the sample. And this is expected because the charge that is flowing in this conductor is never going to see the boundary. It's living in an infinite universe. Are you getting my point? This is your Hall coefficient. And we can write down the Hall resistance of this sample. And what is that? Resistance, RHR, let me call it RHR. It is B times RH. So Hall resistance, in fact, you will see that you will have two components of resistance in your sample. You will have Rxx and Rxy. That you know you can do that. Okay? So what you see here, you see that the resistance, the Hall resistance, is equal to B by, what is RH? It is Qn. So what's happening here? Hall resistance is dependent on the magnetic field. Hall resistance is? It is dependent on the magnetic field. And Hall coefficient is independent of the geometry of the sample. Okay? So these are the two realities that we perform in the laboratory. We can calculate the voltage, we can calculate the transverse Hall voltage in the laboratory by simply performing this experiment, this Hall effect kind of experiment. Right? Getting my point? And one man is performing the same experiment. It's not one man, it's a couple of men. I'm trying to translate it into some kind of person is performing this experiment. And the experiment is performed at very low temperatures. It's performed as very low. Now you see, Hall resistance, it's dependent on magnetic field. Okay? That means as long as there is magnetic field, there is Hall resistance. That means there is continuity. You remember that ball? If I threw a ball, classically, it has all energies. It has continuous energies. It has continuity in energies. And the same thing is happening here, classically. It has all possible resistances. Okay? Because your Hall resistance is dependent on the magnetic field. Now, as long as there is magnetic field, there is Hall resistance, isn't it? It's like I tell you that an electron revolving around the nucleus has all energies. It's like the electron in an hydrogen atom has all energies. It's like the charge is not going to lose any energy. It will not have some definite energy levels in which this electron can exist. That is what means here for the resistance. That the resistance will have all possible values. But the Hall coefficient is independent of the geometry of the sample. Now the person is performing an experiment, and certainly that experiment is more advanced. They are not using a pure sample You know the other things about this Hall coefficient. If the Hall coefficient is negative, because you can extend it to the semiconductor samples. If the Hall coefficient is negative, you will say it's an N-type semiconductor. If the Hall coefficient is positive, you will say it is P-type of semiconductor. You know all of these things. But what am I trying to focus here is that you are performing an experiment. I will not be talking about the actual experimental setup, but you are performing the same kind of experiment at very, very low temperatures. And you have a control that's called a gate control. You must have gone through the MOSFETs. This experiment was performed on a MOSFET in which you have a gate voltage, and the gate voltage has a layer. It's in the form of silicon dioxide, and this layer is treated as a two-dimensional gas. Are you getting my point? And the person is performing the experiment, and he is obtaining strange results. People call it the straight line ever drawn in the field of experiments. Because this is telling you that you have the constant increase in the resistance. Okay? But you are not observing this kind of behavior. You are observing something. You are observing something like this. Oh, this is so fabulous. And this is somehow you call it as the resistivity. Because resistivity has a connection with the resistance. So choosing this as resistivity, what's going on in this graph? Do you find anything strange in this graph? Yeah, there is strange things. The strange thing is, if I think this is a magnetic field, for the sake of argument, you have magnetic field, but the resistance of the sample is constant. Yeah, I'm getting my point. It's something, once I reach at this point, there is a jump. There's a jump, there is no resistance, there's a jump to the next level, then you have another resistance. Then there is a jump, then you have another resistance. This is what is called the straightest line ever measured in the laboratory. And the beauty of this line is it contains the universal constants. Something like Planck's constant and something like charge of electrons. Right? So what is happening here? How is it different from what we were talking about? Discrete resistance. Okay? It's looking like an atom. An electron in an orbit and jumping into another orbit. So you are translating your quantum mechanics, which you are talking at the level of atoms and electrons, you are finding its implications in the bulk materials. In there? No doubt, they are very, very low dimensional. We call it two-dimensional gas. But this two-dimensional gas is a macroscopic system. It's a big system. It's a bulk system that I started with. I talked about the bulk materials. I said how we treat electrons in the bulk materials. Even though we use quantum mechanics to solve these bulk materials, but we have certain assumptions. These assumptions lead us to these band structures of these materials. But what is happening here? you are performing this experiment at very, very low temperatures. But there is another important thing. You are using a very, very strong magnetic field. It's not a magnetic field that we are using in the laboratories. We have those shoes. We are using very, very strong magnetic field using superconducting magnets. And when you have these two conditions, one, low temperature, two, very strong magnetic field, your experiment gives a result like this. We'll be talking about it, okay? It gives a result like this, and the result suggests to us that the resistance of that two-dimensional gas under consideration is quantized. And your system, your macroscopic system is trying to behave like an atom, I will say. That is the basic argument of integral quantum Hall effect. And this is why a Nobel Prize was directly given to this person who obtained this condition in the laboratory. Right? So I think we'll stop here. So in our next interaction, we will try to talk about this integral quantum Hall effect. But till now, we have realized that what's the difference? How to make it different from the classical Hall effect. Any questions? Huh? So okay, thank you all.
So can we say
Yeah, stop. Yeah.
Can we say resistance increases when we increase the magnetic field?
Yeah, you can say, but yeah, resistance is increasing. But that resistance is increasing in steps. See, from this point to this point, there is no resistance. It is not choosing the continuity in the resistance, it is jumping. Getting? So here, suppose this is energy level 1, this is energy level 2, you have an electron. It will not exist between this point and this point. The electron will directly exist at this point. So you will not have, when I'm drawing it like this, I'm drawing it like this, this means there is no resistance. There's a jump in the resistance, right? And this is called a plateau. Your resistance is constant. You keep on increasing the magnetic field, but what is happening to the resistance? Or resistivity, what you say, depending on the geometry, what is happening to that? It's remaining constant. So it's against this rule. You increase the magnetic field, you will have a very different kind, you will have a resistance, okay? So this is what makes it important. This is what makes it surprising. And the beauty is that you have a way to connect this system with the macroscopic systems. You are trying to explain your macroscopic systems using quantum mechanics, using quantum mechanical laws. Okay? So, okay, we'll stop here. Hello?